Welcome to chemistry. Today we're going to be talking about valence bond theory. Here's a little introduction and then some examples we'll be following. Okay, valence bond theory is based on valence shell electron pair repulsion, or VSEPR for short. So this VSEPR valence bond theory gives a three-dimensional shape of a molecule based on the electrons repulsing each other. It's like the two ends of a magnet, which are the same ends, moving away from each other as far away as possible in a three-dimensional space. Okay, what I like to use is an axe for this. Okay, and axe will give us what our shape is. So hold on to that axe. So here's our axe. The A for the axe is our central element. The X is the surrounding elements. The E are the lone pair of electrons only on the central element. Lone pair of electrons on the X's do not count for this. So we are only looking at what's around the central element. So here's our central element. That's A. There's only one A all the time. And we always have this plus sign when we were doing the Lewis dot structures. There's that plus sign. So we can place our elements around this A. So there's one of the elements, here's another one, here's another one, here's another one. We can only have four, that's all we got. We can replace the X's with E's that are lone pair of electrons on the central element. We can also rip off another X and replace it with the lone pair of electrons as well. So let's see how this works. Okay, so we're going to get this generic formula, which is an axe. The A is the central element, the X's are the outside elements, the E's are the lone pairs only on the central element. Okay, so some examples of molecular geometry and just a reminder about the axe there. So the first one is a linear-like structure. You should see that it's A, X2. That means there are two elements outside of the A that are attached to the A. And that leads to a linear shape. And here's an example of that. Hopefully you can see that. It's linear. That's why it's linear. Okay, the bond angle here is 180 degrees. Okay, so that's a linear shape. Now, the next one is going to be a trigonal planar structure. There's one A, like always, and then there are three elements that are attached to the A. So that's why it's AX3. Okay, and here's what the trigonal planar structure looks like. Notice that all the elements are within one plane. Even the central element is in a plane. But it's trigonal because there are three outside elements. So if you look at the green ones, those are the three outside elements. Okay? And then what we have is a planar structure. The bond angle here between this outside element, the central element, and the next outside element is 120. Just like if you were to take 360 degrees of a circle and divide it into three. So hopefully that makes sense. The next one is that we're going to take away one of these bonding pairs here and replace it with the lone pair of electrons on the central element. And so this here represents a lone pair of electrons on the central element. That is actually a bent-like structure. So this bond angle is less than 120. How much? I don't know exactly. Okay, but the structure, the generic structure is A for the central element, X2 for the elements on the outside attached to the central element, and E for the lone pair of electrons. Okay, hopefully that worked for you. The next one here, you notice that E for the lone pair of electrons, and I've kind of highlighted it in that picture. Okay, we'll talk about polarity another time, but this angular or bent structure is always polar. Okay, another set here is going to be here, and this is tetrahedral. Tetra is for four, so that's why the generic structure is A in the central element, and X4. So tetrahedral looks like this. This is tetrahedral. The black thing in the middle is the central element. That's the A. And the white things on the outside, those are the X's. The gray things here are the bonds. That's the pairs of electrons bonding the central and the outside elements. Okay, the bond angle on this is 109.5 degrees. That is the white things are at the corners of a tetrahedron, and they are as far away as possible. And that's why it leads to 109.5. So if we were to take away one of these atoms, that is, let's say, the white one that I'm holding right now, and replace it with the lone pair of electrons, we're going to get a trigonal. See the white, that's trigonal for 3. Trigonal and pyramidal. Okay, the blue thing in the middle is the A. The white things are the X's, and the E is this kind of tannish looking thing that I'm holding on to. So that's trigonal pyramidal. So it's AX3E. This has bond angles that are less than 109.5. Okay? And then the next one, if I were to remove another pair of bonding pair and replace it with lone pairs of electrons, then I get this type of structure here. Kind of looks like a Mickey Mouse, if you will. Okay? But this is bent. It's AX2E2. I'm holding on to the lone pair of electrons. The red thing is the central element. That's the A. And the two white things, here are the two white things I'm holding on to now. Those are the X's. And this has less than 109.5 degree bond angle by far. Okay? Now, some of these structures here are polar, and that is the trigonal pyramidal, that is this one right here, and the bent-like structure is polar, based on just the shape of it itself. So that's it, just a quick little introduction to VSEPR, geometry, and we'll do some examples next time.